Hello, today I'm going to take you through the four major types of chemical reaction. I'm going to show you a synthesis, a decomposition, a single displacement, and a double displacement reaction in this video. I want you to play along though. This isn't one to just watch passively. You should print out or have handy electronically your worksheet here because you're going to be asked to pause the video at various points, fill in some of the blanks, and then resume the video to see if you were correct. Now, no one's going to mark this and no one's going to see it, and so it's really up to you to make sure that you were on the right track. If you get all the questions right, then that's great. It means you're doing well. If you get them all wrong, that's fine too, as long as you can figure out from the video where it is you were making your mistake or what concept you were missing in that case. If you can't, then that's your cue to contact me or your teacher in order to get help before moving on. So, before we begin, let's put on our virtual goggles and we'll get going. In this synthesis reaction, we're going to combust magnesium metal with oxygen in the air to form magnesium oxide. We will do that by placing the magnesium ribbon here into this crucible, which can take high heat, and then inside the fume hood, we're going to heat it up until it combusts. In this first reaction, we are going to react metallic magnesium with oxygen gas to produce magnesium oxide. And so to write that out, we know that magnesium metal is just magnesium by itself, and we're reacting that with oxygen gas, which is diatomic. So that's one you kind of got to remember off the periodic table, that it comes in pairs, oxygen in nature, and so it's O2. And that's going to produce magnesium oxide. And so magnesium oxide, how do we put that together? Well, I'll use the crisscross rule here and say that I know magnesium from where it is on the periodic table gives away 2 electrons, and that oxygen needs 2 electrons, which means they can go together in a 1-to-1 ratio. And so I get MgO on the product side. Now, this is not balanced. I have 1 magnesium on the reactant side and 1 magnesium on the product side, and I have 2 oxygens on the reactant side and only 1 on the product side. So how I like to balance things, I'll go the long route here, is I like to list out my elements that I'm dealing with, and I make a reactant and a product side, and so I have 1 and 1 and 2 and 1. And so how could I get this to be balanced? Well, I need to turn this 1 into a 2, so I can do that by putting a 2 in front. So that changes that, that's balanced, but it also changes my magnesium, so now this is unbalanced, but I can fix that by putting a 2 in front there. So sort of just by inspection, I went through and balanced this out. So there we go. We have our balanced equation. And now I'm asking you, what does this equation mean? And that's something I want you to think about here. What is it? What do these things mean? And so what this means here is that we are combining magnesium and oxygen to form magnesium oxide. Now that may not sound like much, but the key here is combining. We're putting those two things together. We're synthesizing magnesium oxide here by squishing those two elements together. And so that's what that equation means. When you look at that, you can hopefully clearly see that we're starting with two things. They're going together to make one thing here in the end, magnesium oxide. The first thing we need to do is get the mass of the crucible. And we find that it's 12.42 grams. And then we will add the magnesium. And see, the total is 12.47 grams. So now we need to figure out the mass of the magnesium. So I hope by watching the video, you got that the mass of the crucible by itself was 12.42 grams. and that once the magnesium was in there, we get 12.47 grams. And so calculate the mass of magnesium metal in grams. I hope you could see that if you take the mass of the two together, the magnesium in the crucible, and subtract off the crucible, you'll get the mass of the magnesium, which is 0.05 grams of magnesium there. So that was just a simple subtraction.
Now that we have the mass of the magnesium about 0.05 grams, we will now combust it and see what we get for magnesium oxide. Okay, we've seen some combustion. Now I just need to turn off the heat and we will weigh the magnesium oxide. It's still going. We can see that the magnesium oxide is sort of a white powdery, almost looks like ash after the combustion reaction is taking place. We're going to let the crucible cool for a couple of minutes on the countertop here before we take its mass. But I want you to take a guess now. Do you think it's going to weigh more or less after that reaction? Think about what it means to be a synthesis reaction. Okay, now it's time to weigh the magnesium oxide in the crucible. And look at that, we get 12.50 grams. And so that implies that the magnesium oxide weighs more than the magnesium by itself.
So now you've seen the reaction. I hope you saw that there's some evidence there that there was heat produced, heat and light in the form of sort of a fire, and a color change here. It went from metallic to a white flaky look. And so magnesium here, what you've seen here is the same thing that's in sparklers. So if you have ever used a sparkler, it lights up quite nicely. Those are very tiny little pieces of magnesium. And same thing if you ever watched Survivor or used a flint, the metallic part that they use to try to light is magnesium as well, because once it gets going, it burns quite readily. So, have you made a prediction here? Will the mass of the crucible be plus the magnesium, sorry, be greater than or less than it was before? Now, the crucible should stay the same, but so it's only a matter of asking really, is the magnesium oxide going to be heavier or lighter than the magnesium by itself? And I hope that you can think about that if we combine things together, it should weigh more than just one of the things by themselves. And so, whatever your prediction was, there's no right answer there. It's just a prediction. But the answer is that it is heavier because it's combined with oxygen now. It was magnesium by itself, and now it has attached some oxygen to those magnesium atoms. And so it should weigh more. And that's sort of the key, that this is a synthesis reaction here, that we know for sure that those two things went together because the product weighs more than the individual reactants themselves. And so we're going to weigh the crucible next, and we find that it is 12.5 grams. So we've weighed the crucible and it weighs 12.50 grams. And so now we want to calculate the mass of the magnesium oxide. And so how do we do that? Well, we take the new mass of the crucible plus the magnesium oxide, and then we subtract off the crucible again. And we get then that the magnesium oxide is about 0.08 grams. which is more than just the magnesium by itself. That was 0.05 grams. And so now I'm asking you, if you've gotten this far, I hope you can figure out that the oxygen then must be 0.03 grams. If the magnesium oxide is 0.08, that's 0.08 grams, and we know that the magnesium was 0.05 grams, well then that means that 0.05 grams of magnesium must have reacted with 0.03 grams of oxygen in order to create that new compound, magnesium oxide. So, create a statement about how the masses of the reactants relate to the mass of the product. Well, in a synthesis reaction, there's things going together to form the product. So, the masses of the reactants add up to the mass of the product. And again, that's sort of shows you that's evidence of the truth of these two elements coming together to form the product, which is the essence of a synthesis reaction.
Here's the setup for the decomposition of water. This is the power source that will supply 200 volts of electricity to flow through this water setup here. And if you look close, you can see that these tubes are full of water, and we will see that the electrodes down here is where the bubbles will form.
So now we're on to reaction number 2, and this is an electrolysis reaction. You've just seen the setup here. And so what we're doing is we're taking water and we're going to run electricity through it. So we're providing some energy here to break up the water into its two pieces, which is hydrogen and oxygen. And so in this case, we start with the reactant water, and it's going to make hydrogen gas, which is diatomic, and oxygen gas, which, as we saw in the first reaction, is also diatomic. And so we have this sort of the reverse of a synthesis reaction. A decomposition reaction takes something that's a compound and breaks it up into its pieces in their simplest form here. And so is this a balanced equation? No, it isn't. So let's do our two elements here in this reaction. We have the reactant side, the product side. I have 2 and 2. That's good. And I have 1 and 2. And so the oxygens here aren't balanced. And so if I want to get 2 oxygens on the reactant side, I need to put a 2 in front, but that means I've doubled my hydrogens as well. So I now have 4, which means I also need to put a 2 there, which now balances everything out. Again, what does this balanced equation mean? Well, it means that a compound, in this case water, is broken down into its elements, hydrogen and oxygen. And so again, you can see that from the equation that we're taking one chemical and breaking it up into two pieces. And in this case, it's hydrogen gas and oxygen gas.
Okay, let's go.
So now that you've seen the reaction run, there's a clue that points to the reality of the balanced equation above. Let's just go back and take a look at that. If you look at this equation, you can see that we should be making twice as much hydrogen as oxygen. There's a 2 in front of that hydrogen and nothing, a 1 in front of the oxygen. And so we should be making twice as much hydrogen as oxygen if this balanced equation reflects reality at all. And if you look at the two, you can rewind if you want, go look at the two upside down cylinders, and you can see that the hydrogen side, there's a lot more gas in them. It almost looks like it's more than double, to be honest, but in a perfect world, it would be double. But we can definitely see that there is more hydrogen than oxygen. So the visual evidence here is that there is more hydrogen produced than oxygen as the balanced equation predicts. And so those balanced equations really do mean something in reality, and that is something that you can really see in this decomposition reaction. What is the evidence that a reaction took place? Well, a gas was produced. Actually, two gases were produced. Those weren't there before. They weren't in the water. It wasn't carbonated water or pop or something. So two gases were produced. That's the evidence that that water changed from one chemical to two different chemicals, in this case, hydrogen gas and oxygen gas.
So this reaction's been running for about 15 minutes now, and we can clearly see the reality of the balanced equation. One of the tubes looks much fuller than the other, and that one must be the hydrogen because we're producing twice as many hydrogens as we are producing oxygens in this decomposition reaction. Just to finish this off, watch what happens when I turn the power off. You can see that at the electrodes, the bubbles have stopped. This next reaction is a single displacement reaction involving aqueous silver nitrate and the copper from this copper penny. So this reaction's been running for about 35 minutes, and we can see now that the silver that was in the silver nitrate solution has come out of solution and grown these beautiful crystals on the penny. Why they are crystals like this is that the silver is built up, it comes out of the solution basically one atom at a time, the same way frost is formed, one H2O molecule at a time, and it builds on itself in these sort of hairy filaments. I also want you to note the color of the solution. It's gone from a clear liquid to a blue color, which indicates that the copper from the penny has displaced the silver and now is in solution along with the nitrate.
All right, you've just seen the third reaction here. We saw that when copper was placed in a silver nitrate solution, that we get this nice, beautiful silver crystals formed. And so before we get into balancing the equation, because copper is a transition metal, we don't know how many electrons it's going to give away. And so to balance the equation or how it's going to combine with other things here on the product side, we need to know what ion here is produced. And so you should have seen, or at least, this color is somewhat subjective here, but you should have seen at least a bluish color of the liquid after the reaction ran. And that's an indication that we're making copper 2 plus here. That it's not the copper 1 ion, it's copper 2 that is produced. And copper 1 is a different look. It's not blue the way copper 2 is. And so that's one way we know when we're doing chemistry what we've made or what is being produced in a reaction. And so now that we know that, that can help us balance this equation. So it says when copper is placed in a solution of silver nitrate. So we have copper, again, copper metal, like the magnesium is just copper, plus a solution of silver nitrate. And so silver nitrate, if we want to crisscross that, we know nitrate is a -1, so it needs 1 electron. Silver gives away 1, and so we get just NO3. And that's going to produce pure silver solid and aqueous copper nitrate. So we make our pure silver solid, and then because we know it's copper 2, it's going to have 2 electrons to give away here, but nitrate still only needs 1, so we crisscross that. We get CuNO3 2. So there we go. That's not quite balanced, and so I will do that by putting a 2 in front of here. That gives me 2 nitrates, and a 2 in front of there, 2 silvers, 2 silvers. So what does this equation mean? Well, we can look at this and see that we had copper by itself and silver with the nitrate in the reactant side originally, and then after the reaction took place, we now have silver by itself and copper with the nitrate. And so copper displaced the silver. And so sometimes these are called replacement reactions, single replacement. You might see that on the internet somewhere. So displaced, replaced, same thing. That basically the copper kicked out the silver and joined the nitrate, and now the silver is by itself. So what does this equation mean? It means that copper displaced or replaced the silver to combine with the nitrate, leaving silver metal by itself. So something along those lines. But you can really see that by looking at the equation that the silver has left the solution. It certainly came out, you could see it, and the copper is now with the nitrate. So now that you've seen that and you've answered the first couple of questions, what does the solid silver metal look like? Is this what you thought it looked like? So this is really up to you to tell me, but most students, in my experience, don't expect the silver metal, when it's displaced like that, to look like these filaments. But as the video explains, they do come out one at a time, these atoms, and build themselves up into these filaments. So really this is up to you, whatever you say there, yes or no. Basically, you tell me what you thought it might have looked like to begin with. So this is really up to you what you put there. That's a opinion question. So we see the silver that was displaced from the solution, right? It's clearly there. Where did the copper from the penny go? And so this question, I hope, is obvious to you after watching the video, but the copper is now in solution. It is dissolved into the solution and is with the nitrate, hence the blue color. So the copper is now in solution. And so, like the silver was to begin with, the copper is now with the nitrate dissolved in the solution. It's a couple days later, and I've cleaned and dried the silver metal, and so as you can see here, it truly is little shards of silver. So this now goes into my retirement fund. This next reaction is a double displacement reaction involving aqueous silver nitrate and aqueous sodium chloride. So I'm going to prepare the sodium chloride by adding about 100 milliliters of water and a scoop of lab-grade sodium chloride. Now, something I want you to notice is that when this dissolves in, the liquid will be quite clear. Unlike, say, seawater or when you use commercial table salt, there's silicates and other impurities in there,
which make the salt water look cloudy. But when you have pure sodium chloride, it dissolves in completely. So we're almost there. And so if you take a look at that, that looks quite clear. And I've already prepared the silver nitrate by pouring in about 5 milliliters into this graduated cylinder. So 2 clear liquids, and watch what happens when we react the two together. Here it is again in slow motion. So I want you to notice how this precipitate forms, and it looks a lot like smoke filling up a room, and that's due to the very tiny particles of solid that are formed as the two liquids meet.
Okay, last reaction. So you just saw the silver nitrate and the aqueous sodium chloride, which is really just salt water, combined, and they formed a nice precipitate, which is the silver chloride. So let's write the balanced equation for that. This one I've written a little bit strangely so that you have to pick out the reactants and pick out the products here. It says 5 milliliters of silver nitrate in solution produces sodium nitrate and silver chloride when mixed with 100 milliliters of aqueous sodium chloride. And so here are our two reactants, silver nitrate and sodium chloride. The order, of course, does not matter what you write these in. You could write NaCl first if you'd like. And it says it produces sodium nitrate and silver chloride. Sodium nitrate, sodium is one electron to give away. Nitrate needs one, so they go together 1 to 1. And silver has one to give away, and chlorine only needs one. And so they go together 1 to 1 as well. If you look carefully here, that is already a balanced equation, so there's nothing else that we need to do. If you have trouble with that, though, please get help before moving on. So what does this equation mean? Well, we can look at it and see that there's two sets of partners, and they create two sets of partners, but they've switched. And so what this equation means is that the compounds switch partners to become new chemicals or new compounds themselves. Whatever you'd like to, however you like to think about that. But in this case, we went from silver with the nitrate and the sodium with the chloride to now the sodium's with the nitrate and the silver is with the chloride. If you're wondering how do you know what goes with which, you have to think about, without worrying about the numbers, just remember that as in an ion form, the metal will be positive. And again, it doesn't actually matter. It matters for combining, but for thinking about what's going to go with what, it doesn't. And that the second half of the compound is the negative ion, and so the positive and positive won't go together. Silver won't go with sodium because they're both positive, which means they repel each other. And so the only real option for silver to go with, if we're going to make a new chemical here, is the chlorine or the chloride, and the sodium then will go with the nitrate to form a new compound.
So we can see that a precipitate has formed. Now this might just look like a white milky liquid to you, but in fact it is a bunch of very tiny grains of a solid that are sort of suspended in the liquid right now. If we let that sit, they will settle out and sink to the bottom where you can really tell that it is sort of a powdery solid. So when you think about it, when a solid forms, when you hear that in chemistry, you shouldn't think about like a big rock or something like that. It's actually very tiny grains which precipitate out in the same way that all the water doesn't fall out of the sky at the same time. It falls in tiny raindrops. And so the same thing is true of a solid forming in a double displacement reaction.
So what is the evidence of a chemical reaction? In this case, a precipitate formed. So you saw that it was pretty much instantly it turned white, and it sort of again looked like smoke filling up the room. That's the fine particulates of the solid that formed. So you just saw that solid being formed, and I know I've already talked about it in the video here, but I want you to write this down in some form so that you have it in your mind that when a precipitate forms, it has solid forms or something like that. I know when I think about that, or the first time I thought about it, when I think about a solid, I think about something like a rock or an ice cube or something like that. But that's, of course, not what happens. You don't put these two things together, and now you have a block of something. The precipitate forms a very fine powder, which is a solid, and you're about to see in the video that it really is separate from the solution as it will settle to the bottom. So you should think about a powder as opposed to a block or something like that. But you'll see that a lot in chemistry where the word problems will tell you something about precipitate forms. So I hope you can visualize that now a little better as a solid being a very small, tiny particle of solid, not a giant block.
It's a couple days later, and we can see here that the precipitate, the silver chloride, has all sunk to the bottom of the beaker, clearly showing us that it was not soluble in water and that the precipitate is not part of the solution. Okay, so you've seen all four major types of chemical reaction. I hope that helps you visualize things a little better and gives you a better connection to when you're reading a word problem to what happens in real life. Something I do want to caution you on is that we've only seen an example of each of the major types, and all of them have subtypes, and so not all double displacement reactions are precipitation reactions, let's say. There's other types as well, like an acid base, some other things like that that won't quite look the same, but they are in fact double displacement as well. So you've seen an example, but not all in this video. If you have any questions or if you're stuck on any of this, please get in touch ASAP. Don't move on in the unit until you've spoken to me or your teacher so that you are clear on both the concepts and the skills like balancing equations, spotting the evidence of a chemical reaction, so on and so forth before you move on. So I'm going to go count my silver and I'll see you in the next video.